And I'll even show you what it'll always turn out to be, by the way, not just the same. It'll always be this when I'm done. So the composition says I'm going to go F, and then inside here, I'm putting in like PEMDAS. Inside the parentheses, G of X, that's this. So that's 1/2 X plus 1/2. And now I'll look for the F function, which is here. So that 1/2 X plus 1/2 is there, but it's also got to be here. And don't forget to subtract 1. And then I'll distribute. And I get plain old X plus a 1 and a subtract a 1. And then I'm down to X. Okay, well, that's interesting. Meaning, I get, right now, it's not that interesting because you say, okay, what's the big deal? I said these two are going to be identically the same because I know I set it up this way. You didn't know. If they turn out to be the same, it'll always be X, by the way. That tells us something very special about the functions, and that's what I'm getting to. So let's see if this really is the same as X. Okay, F of X is back up here, so go 2X subtract 1. Okay, now I'm looking for the G. The G is over here. So I'm going to go the 1/2, and wherever I see an X right there is going to be the 2X subtract 1. So I got to start with the 1/2, and then I'll do the parentheses, and now I'll put the 2X subtract 1. Don't forget the plus 1/2 at the end. And now I'll distribute. 2 times 1/2 is just plain old 1, so X subtract 1/2, and I still got a plus 1/2, and there you go, just like the other one. You end up with X. So that's unique. Unique meaning that something's interesting about the two functions. We say those two functions are inverses of each other. Whatever that means, that they are very special. There's a relationship between the two. And that's what I'm going to explain to you, what that relationship is. So there's something special about these two things right here. Well, first of all, they're lines, but there are other functions that are not lines that have the special relationship called inverses. So now the definition. All right, so you got to start with two functions. If you have something that's not even a function, forget it. Like a parabola, right? It's not even a function, so forget it. It's got to be a function to start off with. So if you have two functions and you do this composition and you get the same thing, right here, you get the same thing, and I'm just giving you a hint. I've never, ever, I don't know, Bonnie, did you take my math 27? Bonnie?
No, I took 58 and 25.
From me? You take 1A from me? Okay, in your 1A, I think it was Tom, right? Tom Falbo?
Mm-hmm.
Did you come up with, did he go over compositions at all? Do you remember?
Yeah, probably.
Yeah, I don't know. I don't know if this is something that he addresses in his 1A about inverse functions, you know, in the I know that there's compositions that I do in my 1A. I don't really remember or needing to talk about the inverse. So where does inverses come back into play? It might be beyond third semester calculus. I've not taught third semester calculus for a long, long, long time. So where is it used? Why is it used? Right now, I don't have an answer for you for students, not Bonnie, but for students. It's just, oh, interesting. Okay, inverse notation right here, notation. This is called an inverse notation. That is not a power. I'll zoom in so you can see that. You don't say that's f raised to the -1 power. It is not. This is not equal to like whatever 1 over, say, f. And just like this isn't multiplication, that's not multiplication. It's a function. It's not this. No, it's not. It's a notation. It's called inverse notation. And in your trig, which we'll get to, no, not in this class, you'll eventually take a Math 58. If you look at the calculator screen, let's see if I can get the glare off. Right where the sine, cosine, and tangent are, there's these things in blue, for me, that has little -1s on them. That is not a power. Those are talking about inverse trig functions. Inverse functions. So it's very different. It's just the notation. They're inverses of each other. And it turns out the domain and ranges. So if I made a table of values right here, here's an idea, table of values. Let's see, okay, so if x is 0, y is -1. You see what I just did there? Made a little table of values. What's another one? If it's 2 right there, okay, if it's 2, that's 4. This would be 3. If I went over here, x and y, what this is saying is the domain is the range of the other one. Oh, the domain here is the range over here. This should be -1 and 3 over here, and the range is the domain over here. Oh, this should be 0 and 2. Let's check it out and see if it works. Put in a -1 right here and see if you get 0. Oh, -½ plus a half is 0. Yeah, it does. How about 3? Okay, 3 halves plus a half is 4 halves is 2. That only happens when you've got functions that are inverses of each other. So they're just that. If you compose the two, you get this. Visually, you guys remember visually about symmetry? Odd and even function. I mean, remember the words? Okay. An even function has symmetry with respect to the y-axis. Okay, that's an even function. But by the way, that even function doesn't have an inverse because it's okay, here's the idea. It's not 1-to-1. What? What's 1-to-1 mean? Passes the horizontal line test. There's a key right there. If you thought about functions, there's lots of functions, and it does not pass the horizontal line test, then there's no inverse. Parabolas do not have an inverse function. Oh, how about a square root function that goes like this way? It doesn't come back around. See, it doesn't come back around. That has an inverse. So there's symmetry to it. And I'll just show you kind of a picture right here. You know, here's a square root function. So I'm saying it's a function because it passes the vertical line test, and it has an inverse because it passes the horizontal line test. See, it doesn't come back. So it has an inverse. So what the heck is it? Well, that's the thing that I have to show you how to figure out how to find the inverse. Because if it has the inverse, then it has this line of symmetry. Doesn't that feel like the line of symmetry is the origin? Remember that line that goes right through the middle right there at a 45-degree angle? It's got this line of symmetry, and so it'll look like this. This piece right there is F inverse, where this piece right here was the original. You just have to come up with the equation of that thing right there. And that's what I'm going to show you how to do. So, all right, so here's an idea. Isn't that a line? Okay, got to pass the horizontal line test. The only one that doesn't pass the horizontal line test is the horizontal line. I'll say it again. The only function line that doesn't pass a horizontal line test is the horizontal line because it touches a lot of place everywhere. This is a line. It has an inverse. I'm just going to circle it. Does it have an inverse? Yes, just by the nature of any line. Is that a line? No. Does this have an inverse? Maybe. I'll put a question mark. I don't know. I have to look at that. You know what the picture of that one is? Devin, you know what the picture of this thing looks like if you graph this?
The parabola, isn't it?
It is. Well, that doesn't have an inverse. So no inverse. Why? Because if it looks like that, it doesn't pass the horizontal line. It fails the horizontal line test. So no inverse. How about this one? I don't know. I don't know. Well, okay, square roots, I have kind of a feeling about square roots. I think yes. But if you really want, you'd graph these. I'll put a question mark. So these, you'd have to probably graph. Putting a graphing calculator, you probably have to look at it. And if it looks like it's got wigglies, like here's one here. There's a function. Does this have a inverse? Because it doesn't pass the horizontal line test. It goes through it more than once. So this one doesn't. So you'd have to graph each one of these visually and see if there's any like bumps or turns. And if there are, then it doesn't have an inverse. If there's not, like this one, there's not. So this is going to be a yes. I'm looking at time as well. Look at that with the graphing calculator and let's see. Yeah, I'll do this one. I'll do this one. This will be the only one I'm going to do today because of just time. Because this is the 4-step process in order to find it. So if I do one, you can look at the textbook. He's probably got 3 or 4 there as examples. So I'm wondering if this is, so I would put it in my graphing calculator, y equals I want this one here. That would be x to the 3rd, and that was a +1. So I'm going to go zoom standard like this. And you might say, whoa, there's a little dippity-doo-dah thing right there. I wonder if it goes really high and low. So maybe just one time I'm going to zoom in. I'm going to zoom in and kind of see what happens in that area. I just move my cursor right there and hit enter. I'm just going to look. Yeah, it doesn't look like, so it looks like it passes. That's the best I can do. It looks like it passes. So if it passes, we're going to do this. If it passes, that's what I'm thinking it does. To find the inverse, this is what you do. So step number 1, I'm going to replace f of x with y over here. So I'm working on that one. I'm going to go y equals x cubed plus 1. All right, step number 2 says take the x's and y's and just move them around, swap them. Make that an x now, make that a y. Step number 3, solve for the y. So now you got the y in this place. And if you think about swapping the x's for y's, remember that earlier I said, hey, the domain is the range and the range is the domain. So just make the x's y and then the y is x. That's all I did. Make that an x and make that a y. Swap them. Solve for y. Okay, that means I'm going to x subtract 1 is equal to y cubed. And then take the cube root of both sides. So if I do the cube root, you have to put a little cube right there. Now, you don't need to put a plus minus on any odd roots. It's the even roots. When you take a square root, you have to go plus and minus. Don't forget. And number 4. Well, now make the y this funny notation, f inverse of x. And then you're done. You found it, supposedly. Now, supposedly, that's the inverse to the one that's way up here. And how do we check to make sure if it is? Any ideas how we check? And then I'm just about done. How do I know if, in fact, these guys are inverse? What would you do you think, from about 25 minutes ago? Yeah, say it again, Rochelle. Yeah.
You substitute in so that they should, your x's and y's should be opposites. Or,
So,
I mean, your problem number should be switched, kind of.
Okay, so you could make tables of values and put X's and Y's and like do 3 of them and then see if it's reversed, if it works. That's one idea. Or you can do the composition. Now I'm going to do the composition. So I'm just going to do one of them, but you should do both of them. If I do f of f inverse of x, and when you compose this, you should every single time get an x. You should. You have to. If they are really inverse, if you did the math right. So let's see if we do it. Okay, we're supposed to get that. So I'm going to cover that up. I'll go f. Okay, now the inverse is this thing right here. Now we find the f, which is way at the top. Oh, something cubed. It's this thing cubed. It's the cube root. And then plus 1. See, it's this thing cubed. So I put in the cube root of x minus 1. Okay, simplify that. That's x minus 1 plus 1. And sure enough, that gets me the x. Oh, I did it. I was able to find it successfully. Okay. While you're writing that down, maybe I'm going to take a look at your little quiz here. Yep. Okay. I've just released it. You should be able to go into Canvas and open it. Tell me if you can see it. It's called number 4, daily quiz number 4. I'm just looking for heads to go up and down if you can. Rochelle's saying yes. Rochelle's the only one that can see it. Okay, I'm seeing. So go into Canvas under assignments. Okay, Farbod, you seeing it? Okay, good. So, and thank you, AJ, saw your thumb up. So now we're going to do, it's been a while since we've done this. I'm going to put you in groups of about 3, and you'll have the rest of the time that you need before you leave today there's only 5 problems, and to discuss, and you guys can decide which problems you want to, which answers, I guess, individually. You don't have to always agree on the answers, but you got to finish it before you leave, and then Bonnie will be over there waiting for anybody that wants to hang out and answer a few questions. So, Bonnie, any questions or any statement before I release the breakout rooms?
I'm wondering, it looked like there might have been a question for you about the last problem you were working on.
How about if I stick around outside, whoever it was, and then you can join your other members. So if you have a question, just stick around. Who was that, Bonnie?
Devin, did you have a question? No? Okay. It looked like you were about to ask a question and then decided not to.
Oh, yeah. No, you're very observant. No, I was going to ask if the last problem he did in the workbook was called Finding the Composition, but I kind of answered my own question. So thank you.
All right.
Okay, so it looks like 3, and there might be a breakout room of 4. I'm okay with that. More is better for right now with a limited time. Okay, let me see. Bonnie might be in one of these. I want to make sure that I make Bonnie go away. Yeah, so I need to move somebody else in number 7. Okay, I'll take a group of 4. I'll move this person here into breakout room number 4. Good. Oh, that's interesting. That doesn't work. That to number 7. 3. Okay, so there'll be one group of 2 and the rest of groups of 3. That's what it turns out to be. Okay, opening the rooms.
All right, I'll see you later, Jeff.
Okay, Bonnie. Good, always good to see you. We'll talk to you soon.
Sounds good. Bye-bye.